Hi, thank you very much. So the subject of this talk is going to be meso to submesoscale turbulence in the mixed layer of the ocean. And it's about diagnosing kinetic energy cascades, and if it's possible, from mainly surface drifter data. And I'm also going to talk a little bit about satellite data. So this work is a mixture of different research pieces that were actually done by Julia, who already had results yesterday on her poster, and then PhD student Ilma Leimann. Then there was also a master student who worked on this general subject, Emily Bräunig. And then we had support by Moritz, Epke from the modeling side, and then Maren from observations. And I'm going to try to put this all into a storyline and then see if this works or not. Okay, so the difficulty, so this is going to be about basically spectra and spectral fluxes and how to get information about this from observations in the ocean in the mixed layer. And so the conventional spectral methods, they usually really require high quality and usually gridded data. And you don't necessarily have that in the ocean. You have ship tracks from which also spectra have been estimated, but they're basically just tracks in some regions of the ocean, and the resolution is also limited, and you don't necessarily get it at the very surface. Then, of course, you have SSH data, comprehensive data sets of gridded data, where spectra and spectral fluxes has been estimated from. That only gives you the geostrophic component of the flow, and with really barely resolving subdeformation radius scales, even though there's some improvement from the SWOT mission to be expected. But still, it's only the geostrophic component with some aliasing from smaller scales. So I'm going to actually focus on structure functions, which are classical turbulence tools to diagnose scale-dependent energy transfers and energy distributions. So the advantage is they're really easy to use, and they can actually be estimated from ungridded or scattered measurements. And so what we have actually are different data sets of surface drifters, and I'm showing the examples below, so that were deployed during our Transregio project. So we have drifters deployed in the Southern Ocean. So here in Walvis Ridge and Cape Basin regions, then a data set from the Benguela upwelling region, and then there's actually also some that we deployed in the North Atlantic current. Yes, so we want to explore the potential of these drifter data because the advantage is that they can potentially really bridge scales from 100 meters to about thousands of kilometers. Okay. And so what you usually do with Lagrangian measurements or drifter data, you can actually look at dispersion statistics, so pair dispersion. So you look at the mean square displacement of pairs particles as a function of time. And so imagine you have an energy spectrum in the ocean. It goes with k to the minus alpha. So what you would expect is that for steeper spectra, you would get, so alpha greater equals 3, you would get the so-called non-local dispersion, which would be dominated by eddies of scales larger than the separation of the pair. And then the mean square pair separation would go exponentially with time. Then for shallower spectra, you get the so-called local dispersion, which would be dominated by eddies of the same scale as the separation. And then you get the famous Richardson dispersion regime, where the mean square displacement grows cubically with time when your underlying spectra has a slope of -5/3. And later on, you have diffusive dispersion for scales larger than the largest eddies. So typically in or 2D or QG turbulence, if your initial pair separation is down here, so smaller than the energy injection scale, and if your energy spectra goes like k to the -3 and then k to the -5/3, you would expect first an exponential regime that goes into Richardson dispersion, and then later on will be diffusive. So this is just an introduction on turbulence regimes that you can deduce from particles or pair dispersion. And I'm going to just briefly come back to that actually later. But we want to now focus on structure functions. So structure functions that can be computed just simply from the velocity difference as a function of their separation. And you can define them as a total structure function, or you can also define longitudinal or transverse structure function components, depending on if you look at them in the direction of the separation or transverse to the separation. Then you can look at the orders, or the moments of these structure functions. So the second order structure function can actually be related to the energy spectrum. And the third order structure function can be related to spectral fluxes. Okay, so talking about Lagrangian structure functions, it means that, of course, the Lagrangian drifters, they follow the flow in the ocean, so they sample basically the velocity field. And so you can treat these Lagrangian data as scattered velocity measurements from which you can then estimate structure functions. And so very prominent data set where a lot of structure functions were analyzed was the Gulf of Mexico data set. Those were from drifters actually deployed at the very surface. And some studies arose from this showing that they're claiming that they show dual energy cascades, and also actually biases that happen when you compare Lagrangian structure functions with Eulerian structure functions. And I think Han is, going to talk more about this on Thursday, tomorrow. But on the other hand, you actually have the Global Drifter Program data set. So those are drifters that stay at 15 meters depth. So they're different from the drifters that were used in this data set. And not that many structure function analyses were done on this data set, but it's a really technically a comprehensive data set with a lot of data is globally available, so there could be a potential of investigating structure functions from there. So let's start with the second order structure function. So you can relate via Fourier transform the longitudinal second order structure function to the energy spectrum. Then the zero order Bessel function shows up. So from here you can already see that second order structure function is related via an integral over wave numbers to the energy spectrum. However, you can actually look at limits. So you can look at the limits, large and small scale limits of this term 1 minus J0. So for scales larger than the separation R, so for very small wave numbers, this term actually goes to a quarter k squared R squared. And then on the other hand, you can look at the other limit. So for scales much smaller than the separation, then this term actually goes to 1. So taking these limits, you can actually look at this integral as a sum of 2 contributions. And due to this k² term here, you can see that, so times the energy spectrum that has the scaling minus alpha, you can actually see that scales smaller than the separation actually contribute energy here, this term, and then scales larger than the separation and contribute actually entropy. And so you can easily work out these integrals and put in the limits, and then you see that we have some divergence here. So you have to have this condition that alpha is between 1 and 3. But if that's the case, then you can work out the limits, and then you see you have a pretty simple relation. So both of these terms would contribute r to the alpha minus 1. So if you have a spectra that goes with minus alpha, then your structure function should go with r to the alpha minus 1. So that means for your nominal minus 5/3 spectrum, you should get a scaling of 2/3. And then if your spectrum goes with 3, you should get r². Or 2, you should get a linear scaling, and so on. Okay, so now the first part of this is we want to look at second-order structure functions and compare them to spectra. And this is work that was done by Ilma, who's a PhD student. So we are taking the ICON ocean submesoscale telescope simulation for the North Atlantic. So this is essentially a global simulation, but it has a very high resolution telescope that's located basically here in the North Atlantic, in the Gulf Stream separation area. And as you can see, the resolution in this telescope goes down to about 500 meters. And you can zoom in, and what's shown here is the Rossby number. And so this model was run for 3 months from the spin up, and it actually does not include tidal forcing, I should mention. Yeah. So then we divided this simulation into 7 boxes from where spectra and structure functions were analyzed. And we didn't only compute Eulerian structure functions. So Eulerian structure functions are easy to compute. You just take fixed points, and then you compute the second-order moments as a function of separation of the points, right? But we also deployed numerical particles in this model simulation. And the way this was done was actually we explored a multi-scale self-similar deployment method where the particles were deployed in a Sierpinski carpet, which means that you cut out squares in a similar way down to so you can see as a bigger square, and the squares get smaller and smaller, and this is done in a self-similar way. And the reason why you do this is you want to make sure that the initial separations of your particles are such that you actually fill the scale space in the best possible way. So if you would randomly deploy the particles here, you would actually not fill the separation space well enough necessarily. And also when you compute structure functions and you actually use every single point, which you cannot actually do on a model. It's computationally very, very expensive. You have a lot of points. And also, of course, in drifter deployments in the real ocean, you don't have all points. So this is also a way of going into the direction of actually doing the deployments scale dependent in the observations. Okay, so now we're equipped and we can look at some questions that we're asking now. So do we actually find scale ranges with clear power or scaling that would be indicative of actually inertial ranges? And then which slopes do we find? Do we actually find -5/3 anywhere? And then one question is, do the slopes may be shallow for scales smaller than the Rossby radius? And then are the spectra consistent with the second order structure functions? And are the Lagrangian structure functions consistent with the Eulerian structure functions? Okay, now we can look at spectra. So we see that you can actually fit lines to these log-log plots, and you can do this actually for different ranges. So we did fits for the entire range, but we also decided we're using the Rossby radius as a scale, dynamical scale, where we would fit the spectra for scales larger and smaller than the Rossby radius. And so what you can see is that actually we can see a clear power law scaling, especially here for the Gulf Stream boxes that go over more than 1 decade. So south or off of the Gulf Stream boxes, the fitting, so the slopes are more variable. Okay, so all slopes are steeper than -5/3. And the slope in the Gulf Stream boxes is actually closest to -2. And then for the scales smaller than the Rossby radius, you find it's closest to -3 for the boxes that are not in the Gulf Stream region. Okay, now we can look at the structure functions. And what you see here is so the Eulerian in blue and the Lagrangian in orange. So first of all, you also see, so first of all, now small distances, so small scales are on the left, large scales are on the right. And so you can also see we get power law scaling also for the second order structure function, and also as kind of steepening for the boxes that are not in the Gulf Stream. We also can see that there are some differences between the Eulerian and the Lagrangian structure functions. So the Lagrangian structure functions tend to steepen towards the larger scales for a lot of these boxes that have more energy at larger scales. Okay, so now we just compare the fits of the exponents of these lines that we can fit. And so what is plotted here is we have the exponent of the Eulerian structure function and then the corresponding one from the spectra. And here you have the Lagrangian structure functions. And this is actually from a fit over the entire range. So not just the Rossby radius, not taking into account, so from 5 kilometers to 100 kilometers. And so this red line would indicate that the exponents satisfy the scaling relation that we derived earlier. So we see that the structure functions are always shallower than the spectra. And it's actually the Lagrangian structure functions that come closer to the spectra. but there also seemed to be like a linear relation between the structure function and spectra exponents. So now comparing the Lagrangian and Eulerian structure functions. So there are also differences. So the Lagrangian structure functions tend to be steeper than the Eulerian structure functions. Okay, to try to look at maybe some of the dynamics behind this. So of course, the Lagrangian particles, they follow the flow, so they sample different regions than the Eulerian structure functions and spectra might sample. So we can look at actually a Helmholtz decomposition of the Eulerian and Lagrangian structure functions. So what you can see is, so this pink part is the divergent part, and this gray part is the rotational part. So we see that the rotational part pretty much dominates at all scales in all of these boxes. The divergent part becomes a little bit larger compared to the rotational part for smaller scales. But what you can also see is that actually the divergent part for the Lagrangian structure function is always much larger than the divergent part of the Eulerian structure function. So particularly for these Gulf Stream boxes, the divergent part actually goes to pretty much zero for the Eulerian part. And so this is not unexpected, of course, because Lagrangian particles tend to get trapped in small scale as well as large scale structures. So the divergent part actually dominates at all scales for the Lagrangian structures. So what happens, for instance, here is in the Gulf Stream, they get trapped by the large scale Gulf Stream. So previously what was found actually in these Gulf of Mexico data sets was they found biases in the structure functions from convergent structures, particularly at small scales. But here we find actually that the small scales, the Eulerian and Lagrangian structure functions agree better, but you actually get trapping also from the large scales that lead to enhanced divergence in the Lagrangian structure function. So to look in more detail at the slopes, what are the slopes that we're getting for what kind of ranges? So you can look at the compensated spectra actually. So here examples are when you plot them in a compensated way for k to the 3, k to the minus 2, k to the minus 5/3. So what this means is if you see here a horizontal line, then it means this scaling is satisfied for this kind of wave number range. So with these compensated plots, you can more easily see actually which slope you have actually for which wave number range. And so as I've mentioned earlier, this is an example for this dynamically very active Gulf Stream box. You can actually see that the scaling is most consistent with this k to the minus 2 over really a decade. And you can actually look now also at the structure functions. And you actually see that you also get a scaling consistent with this k to the minus 2 for smaller scales, 4 to 20 kilometers. So the scaling is not as extended that you're getting. And then the slopes actually change, and your scaling is more consistent actually with minus 5/3. So it's not unexpected necessarily that you don't get the scalings exactly at the same distances as you got for the spectra, because as we've seen earlier, you can think of the second order structure function as coming from an integral over the spectra. Okay, then another example of a box that's more off of the Gulf Stream. Here you can actually say these two scalings are not very good, but you can get a more prominent or promising scaling actually for the k to the minus 3, so it's steeper for two ranges of wave numbers. So I've already shown that earlier. And again, a similar picture arises for the structure functions, but not exactly at the same scales. Okay, so just to summarize this part, so k to the minus 5/3 is not really fine, but we do have a good slope that we can fit, and it's k to the minus 2, basically in these Gulf Stream boxes for 10 to 100 kilometer scales, and then steeper, more k to the minus 3 outside these Gulf Stream boxes. And so this k to the minus 2, it's consistent what is also in this region found from observations of Gulf Stream turbulence. And you can explain this minus 2 by frontal dynamics in the mixed layer. So, and even in the structure function framework, you can actually show that, imagine you have an area that where you have actually a random distribution of fronts, sharp fronts, then you can show that the probability of a drifter crossing the front, it increases with separation of drifter pairs. And you can actually show that then the second order structure function would scale linearly with the separation. So that would then be consistent with this k to the minus 2. So the structure functions are shallower than the spectra. However, there is actually a linear relation between the two. And so we also found this k to the minus 2 scaling basically, but for a less extended range, and then they shallow to 2/3. And actually the Lagrangian structure function agreed better with the spectra. And it's maybe because they actually tend to sample the dynamically more active regions at all scales, actually. So not only at the small scales. Yeah, so that was summary of that part. And now we're coming to the higher order moment, which would be the third order structure function. So usually when you look at third order structure function and how it's related to the energy transfer across scales, you look at this Kalman-Horvath-Molin KHM equation. So how you get there is you sum the momentum equation for u of x and t multiplied by u of x plus r and t, and the u x plus r and t momentum equation multiplied by u of x and t. So r is then the separation of 2 points. And so then you get at this KHM equation, and you could write it as an equation for the second order structure function. And here are actually included 2 dissipation terms, so large scale friction term and a smaller scale viscosity term. And here this comes from the forcing energy input. And then the important term now is here this divergence of the third order structure function. And yeah, this comes basically from this nonlinear advection term. And now when we then, so here we have not made any really inertial range assumptions. So what comes out is this divergence of the third order structure function. But now we make inertial range assumptions. So we're saying we're far away from the dissipation regimes, and we have a constant energy that is supplied by the forcing that is taken through the scales. And then what comes out is this relation here. It's a quarter this divergence of the third order structure function, and it's then equal to this constant energy transfer. Now you make the assumption of isotropy, and then you can express this divergence operator actually for d dimensions like this. You equate it to epsilon, and then all you do is integrate. And then what comes out for 3D is actually a famous relation that was derived by Kolmogorov. He actually derived it for the longitudinal structure function, so it has actually a different factor for fifths. But what comes out is that the third order structure function scales essentially linearly with separation. So something similar actually comes out when you do it for 2D turbulence. It's a little bit more complicated. So this is a little hand wavy because actually you have to take into account also entropy conservation equation. But essentially this is also the relation that comes out. But here actually the energy transport is inverse. And so your third order structure function would be positive, whereas for a forward cascade, the third order structure function would be negative. So without invoking these inertial range assumptions, you can actually also just take the Fourier transform of this KHM equation, and then you get a relation of the spectral energy flux as a function of wave number, and it's then this integral of this divergence of the third order structure function. And you can actually show, similarly to what we've looked at for the second order structure function, that you can also write this as an integral that involves second order Bessel functions. And you can also invert this relation, so you can also express the third order structure function as an integral over the spectral flux. And now when you actually you can also take limits, as I've shown before, of this, and then you actually see here it's done for the third order longitudinal structure function, that again you get actually contributions from your spectral kinetic energy flux, but also contributions of the entropy flux. So when you interpret especially the sign of these third order structure functions, you have to be a little bit careful maybe, because you also have to take into account maybe entropy flux contributions. So you can actually look at the spectral flux in different ways. So you can do the usual Fourier transform, or you could also look at filtering the equations, as was done by Louis et al. has become quite popular in oceanography. And so basically the equivalent of the KHM equation is of course here the equation for the filtered kinetic energy. And then you actually have this coarse-grain flux that shows up as a function of filter scale. And what you can also actually do is you can express this coarse-grain flux as a function of the velocity increments, so the structure functions. And then you also arrive at a formulation that is like an integral and involves this filter G that is here, just the general coarse-graining filter, and here the third order structure function. Okay. So what simply we now do? I think so. Yeah. Yeah, I'm already. Okay, right. Yes, I'm wrapping up. Sorry. Okay, so I just want to show two more plots. So one is an estimate. So we were taking in the South Atlantic SSH data, and just as a proof of concept or not, you can calculate actually the structure functions from these geostrophic velocities. so in many different bins. And you can compare what comes out from the simple scaling with over R, and you can actually compare it to the energy transfer rate that's from the spectral flux. And what you see is the pattern is actually quite similar. And here the points are actually bins where you see also that the sign of the third order structure function is positive, which is like you would expect for inverse cascade, but there are also some bins where the sign is actually negative. So, and then the last plot is where actually you can also calculate from the same data sets the coarse-graining flux. So what you see here is the Hofmiller diagram. So where we did it for a few years, and it's actually for the region where the surface drifters were deployed. And what is quite striking is actually that this coarse-grained flux, the pattern is actually very similar to this very simple scaling of the third order structure function. And you also see you have, so positive here means inverse cascade. So you have a lot of, this is a 30-day running mean. You have some years or months where you get negative, and it's consistent actually also with the negative structure function. So if you average over all of these years, you get the net inverse cascade, but you have to be careful. And okay, I talked way too slowly, I guess. I was actually still going to come to the drifter data, which Julia already showed on her poster. But so from the drifter data, we're actually deducing a dual cascade regime with actually an inverse cascade, so a positive third order structure function for scales around 20 kilometers and larger. And then we're also deducing actually a negative regime that could be indicative of a forward cascade, even though this is not the regime of 3D turbulence. And this is also consistent with the scaling of the second order structure function with -5/3. So in the drifter data, at least from this region, we do see the slope of -5/3, and that's also actually consistent what we find from ship ABCP data. And I will stop now. Thank you.